Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to take a look at devices. Really quick though, I would like to take a quick second and thank the partners of the channel, Eearslya and Wensheng. The partner is the highest tier of supporter on the channel. And so I just wanted to say thank you to our partners as well as our other supporters that are listed here on the screen. So if you're interested in supporting the channel, there are a couple ways to do that now. First off, I have channel memberships available. You can access that by clicking the join button below this video. I'll also provide a link to a video that I have describing the memberships. And I also have a Patreon page, which is patreon.com/TravisVroman. Thank you all very much for your support. It is greatly appreciated. So more than likely, this is going to be split across at least 2, maybe 3 videos, just because devices are quite long-winded. So just a quick recap. You have 2 different types of devices as far as Vulkan's concerned. There is the physical device, which is a representation of your physical GPU. So it contains information like what features it supports, how much memory it has, things like that. You then have a logical device, which is used throughout most of the system. That is sort of the application's view of that device. So the physical device is required, at least in some stand-up stuff, but once we are done with that, we won't really need it all that much anymore. The logical device is the ultimate goal here. So we have to start with the physical device first. In order to get going with all this, we are going to need to start by declaring some types. So if we go to our Vulkan types INL, we have our context, and above that context, we are going to want to type def a new structure. And we're going to call this Vulkan device. Okay? And our Vulkan device is going to encapsulate both our physical device and our logical device. So in Vulkan, those are VK physical device for the physical device and just VK device for the logical device. So again, this logical device is the one that we're going to use most of the time, but physical device is what is needed to sort of get there. It's a means to an end, if you will. All right, so since we're going to be coming back to this quite often, I'm actually going to leave this open at the same time as the other view here. And we're going to be jumping back and forth between these two. So the next thing that we need to do is under Vulkan, we need to create a new file. And we're going to call this vulkan device.h. And I'm just going to move this over here. Okay. And our vulkan device.h is where we are going to put all of our device information, because again, this is quite a bit of an amount of code here. We want to keep this as separated from the rest of the code as we can. So for now, it's going to be pretty simple. Our typical pragma once and include Vulkan types. We have a device create, which takes a pointer to a Vulkan context, and then a device destroy, which also takes a pointer to a context. So with that, why are we taking a pointer to a context? Because context doesn't know about the device. Well, now it does. Right, so we're going to add our device and store our device on our Vulkan context. Okay, great. So now we're going to have to define these functions. So I'm going to take a copy of these and create another new file called vulkandevice.c. Paste those guys, and then at the top, we're going to want some includes. So I am actually just going to include everything that I believe we're going to need, which is going to be vulkandevice.h. We're going to need our logger. We're going to need some string functionality. We're going to need some memory functions, and we are going to need our darray. So the way that this is going to work is Vulkan device create. If it successfully is able to get through the entire set of operations successfully, it will return true. Otherwise, it will return false. So before we go any further, I'm going to go back to Vulkan backend, and we're going to tie this in now. So right here before our Vulkan renderer initialized successfully, we are going to go ahead and add in our call to our Vulkan device creation. However, because of this, that means that we are going to need a new include at the top. So now we can include vulkandevice.h. and we can go back down here, and we're going to create our device. And again, if we return false here, we're just going to say, hey, we failed to create the device. We can't do anything else. Okay. So now that that's hooked up, we can go ahead and start filling out our Vulkan device creation. Although, I think before that, there actually is one more thing that I want to go ahead and create. So I was going to put this till after, but I think I'm going to do it now, actually. I'm going to go ahead and create the surface, just because I want to get the platform-specific stuff out of the way. So, as I mentioned before, Vulkan needs a surface to render to. And primarily speaking, that means we're going to obtain a surface from our windowing system. And we're going to need that surface in some of these calls for the device creation. So I'm actually going to do the surface creation now before we move back into the device. So I apologize, things are a little bit out of order here, but now that I think about it, you know, sort of doing this a little bit on the fly, these are the kind of things that come up sometimes. So if I go back to Vulkan platform, we are actually going to need one more function, which is going to be platform create Vulkan surface, right? And it's going to take a pointer to the platform state and the Vulkan context. I'm going to forward declare these here so I don't have to have any more includes. Okay. And then I'm going to go to platform Win32, and I will fill that one out first. Right below where we defined our platform get required extension names, I'm also going to define our platform create Vulkan surface. So here is our platform create Vulkan surface. Now, I realize that we're exposing some Vulkan stuff in our platform layer. This isn't ideal. There might be a better way to split this up. I may wind up changing this in the future, but for now, I'm going to leave it as is. But all this means is that I need to add a couple things for surface creation within this platform file, which again, isn't ideal, but if there's any messiness whatsoever, I would most likely rather have it here in the platform layer than the opposite. So if I include here our Vulkan Win32H, which gives us the Windows-specific Vulkan functions, and then our INL file for our types, that resolves most of the errors. And so what we're left with is an error for the surface, which does not exist on our type. Okay, so thankfully that is an easy one to resolve. All we have to do is, right after our allocator on our context, paste in a surface, and that's it. That should fix this. Okay, and so you'll also notice that not only do we have a context surface, but I'm actually storing this as part of the platform state. So if we go up here to our internal state, we are actually storing it there as well. So what I'll need to do is also just keep a copy of it there. Okay, and we may not need that in the future. This is temporary while I'm trying some stuff. I'm keeping it in both places for convenience, but we're probably only going to wind up needing it within Vulkan itself. But for now, this is where I'm actually storing it and creating it. So this is the Win32 version of that. The Linux version of that is quite similar. So up here at the top, for surface creation, we will need to define the VK use platform XCB KHR. And Vulkan actually needs that in order to give us the proper types. And then we include our INL as we did for Windows. In the internal state, we will add a VK surface KHR to that. And then of course, after our definition of get required extension names, we'll go our create Vulkan surface, which looks almost exactly the same as the Windows version. The only difference here is we're calling VK create XCB surface KHR, which is the XCB version of this. And if we look at the Windows 32 version, we are calling VK create Win32 surface KHR. So these are where those extensions come into play to be able to create those surfaces. Okay. And then back in Vulkan backend, we simply hook this up, right? So all we have to do is say we're creating the Vulkan surface, call our platform create Vulkan surface, and if that fails for some reason, we throw an error and return false. Otherwise, we say it's created. Okay, and that's all there is to the Vulkan surface. That's one of the reasons I wanted to knock it out now, because it's nice and simple. And we are going to be referencing the surface within our device creation. So I want to go ahead and, I figured it made sense to go ahead and do that first. Okay, so back to device create. So far we have absolutely nothing in our device creation. And so this is going to require a couple of steps, right? So one thing to bear in mind is when we're dealing with device creation is a bit of a misnomer when it comes to physical devices, because we don't actually create a physical device, we select a physical device, right? So we query the system to say, hey, what GPUs do you have? And then we look through the properties of that GPU to make sure it meets the requirements that we set. And then if it does, we go ahead and select that one or the best one on the system. If there's multiple GPUs, we go ahead and select the best one that is present. So the algorithm behind that selection will wind up changing over time. I'm going to keep it very simple on the high level and just make sure that it meets our minimum criteria. I'm not going to worry about prioritizing devices or anything like that. But eventually we will want to do that. So again, I'm going to start off with a selection of a physical device, which we're going to want to actually place it below this because it's a pretty long function. So I'm going to forward declare select the physical device here. And then under our device create, I'm simply going to call select physical device, right? And if that fails for some reason, I'm just going to return false, which will indicate that we can't create the device, okay? And so select physical device is what we're going to fill out first, okay? So in order to select the physical device, the first thing that we need to do, as I mentioned, is obviously define the function, and then we are going to query for what GPUs are in the system. And let me resize some stuff here. Okay, so we're going to enumerate the physical devices, and this is going to give us a count, and if we have a count of 0, then that means that there are no devices on the system which support Vulkan, which is an immediate failure, right? So we just return false there. Okay. However, if we do have devices, then we are going to go ahead and retrieve those devices, right? So here we're creating a physical device array of the size of physical device count, right? And then we just call physical, enumerate physical devices again. So you're going to see this pattern over and over again where we have to call this function more than once. We call it the first time, passing it a pointer to an integer to hold count, and then passing null for the actual array itself that's asked for here. And then the second time we call it, we pass the count again, but then we pass an array for that. And that's how the function actually knows whether we're trying to get a count or whether we're actually trying to fill that out. Okay. So the next thing that we're going to do is we are going to enumerate over these devices. So that requires a for loop, nice and simple. From that, we are going to be extracting several things. We are going to extract the physical device properties, the physical device features, and properties for the memory. And we're going to use these various bits of information to look at the device to see if it actually fits what we need it to do. Okay, so the next thing is, before we move on, I like to actually store off a lot of this information in a structure that we're actually going to need to use later on. So I'm going to declare a structure up here. And I'm doing it up here because it's internal. It won't ever be used outside this file, so it's okay that we're actually doing it here. This is where we actually store some information about the physical device itself. Okay, and I've got some of the things that we're looking for in here. For example, whether or not it's a discrete or dedicated GPU, whether or not it supports sampler anisotropy. I'm not going to get into that now, but it is something that I want, so I'm going to track that. I'm going to keep a copy of an array of the device extension names that we want. And then I have graphics, present, compute, and transfer. So if you recall in our initial discussions, you have a device which provides queues, which can take commands to be executed in that queue. So a device has several different types of queues for different types of operations. There are graphics operations, which is like drawing to the screen, for example. I should say draw calls specifically, not necessarily drawing to the screen, but draw calls. There is a present queue, which is used for presentation, that is presentation to the screen. There is compute, which is used for compute shaders, and then there's transfer for transitioning data from one format to another, like image data, things like that. We'll get into that later. So these things simply indicate whether or not these are supported. It does not give us the actual indices themselves. It just says, does it have a graphics queue? Does it have a present? Does it have a compute or a transfer queue? Yes or no. It does not actually tell us what those things are. It's just saying, hey, does it support what we need? Okay. So down here, we're going to take that structure and fill it out. So first, we're going to start off by zeroing everything out. And we are going to, by default, set this all to true, right? So this is actually our requirements. This is what we're going to be requiring. We're going to want a graphics, present, and transfer queue. If we need compute, we will set that to true as well. We're also going to mark that we want a discrete GPU and that we want sampler anisotropy. Okay, so these are our requirements. Okay, and then as far as the required extension names that the device has to have, we just need the KHR swap chain extension name for the device extension. Okay, so these are the requirements for the device. If it doesn't have those things, then we'll move on to a different device. So I mentioned queue families before, and now we need something to hold the queue family info, right? And so this is what holds those individual indices, right? So one for graphics, one for present, one for compute, one for transfer. So this is just a structure to sort of easily be able to hold the queue family indices for those different queues, okay? So the next thing we're going to do is start off with a zeroed out structure of physical device queue family info, okay? So the next thing that we're going to do is we are going to use this information along with the current device to check to see if the current physical device meets our requirements. So first, we're actually going to forward declare a function because we want to put this at the bottom. And we're going to need a few things to be passed to this function. First off, we're going to need the physical device itself, the surface that is going to be used, the physical device properties, the features, the physical device requirements, and then our structure of queue family info right here that will contain our indices. And then we also need some swap chain support info. So we actually do not have the swap chain support info yet, so we need to create that first. So I'm not going to talk too much about what the swap chain is. Most of this stuff regarding the swap chain support info will make sense later when we actually build out the swap chain. So with that said, I'm going to go ahead and create a new structure here in Vulkan types INO for our swap chain support info. So first off, we have surface capabilities, which is the various features and capabilities available on the surface, and we'll see a little bit more of that in just a minute. We have format count, which is basically the image formats that we're going to use for rendering. And then here is the array of those formats. And then we have presentation modes or present modes. We have a count and the actual modes themselves. So we're going to need these things to be declared as well when we actually go to see if we have a device that meets our requirements. Okay, so that is everything regarding that particular function. So next we'll go down here to the bottom and we'll go ahead and define whether or not the physical device meets requirements. So this simply returns a Boolean. So we're basically going to look over a bunch of different properties and features and requirements and use those things to determine if the device passed in meets our requirements. So the very first thing that we're going to do is we are going to set all of our queues to -1, meaning not supported, right? Now, I do realize that -1 being assigned to a U32 is actually going to wrap it around, but that's okay because it just means that we have an insane value that doesn't make sense, okay? So I am using wraparound logic there purposefully for that. Okay, so the first thing that we're going to do is check to see if it's a discrete GPU, right? Because that is one of our requirements. So if our requirements discrete GPU is flagged, which in our case it is here, then we're going to check to see if the device type in the properties that is sent in is physical device type discrete GPU. Okay, and if it's not, it's just going to throw some info saying, hey, this isn't discrete, but a discrete one is required, so we're going to skip the device and return false. Okay, so that's basically the way this is going to work, is any of these requirements that aren't met along the way, we're just going to boot out early and return false. Okay, so the next thing that we want is we want to obtain the queue information to fill these guys out. Okay, and so similar to other places in code, we first obtain a count and then we obtain an array, the size of that count with our queue family information, right? And this is full of VK queue family properties. Okay, so we go ahead and obtain all of those from the device, and then we're going to basically take a look at each of the queues and see what it supports. Okay, so we're going to iterate them. Now, I'm also going to sort of build in a little bit of a graphic table here and output some information as to what queues this particular device supports, just for debugging purposes, right? And so I've got here sort of a header row that I've made, which has graphics, present, compute, transfer, and then the actual name of the device itself. Okay. So before I jump too much into this, I want to illustrate something. I'm going to open up a command prompt and I'm going to run Vulkan info. And this will hopefully clarify a little bit of what we're dealing with here. So this actually gives us all of the support information for all of our devices, as well as its support, its memory, all of that stuff, right? And actually, for example, we have our device properties and extensions. So right here we see that we have GPU 0, which is the only GPU I have on my machine. It gives us the device and vendor ID, all that kind of thing. Tells us what type of GPU it is. So we have a discrete GPU here, and it actually gives us the device name, right? We also have in here somewhere our queue information. Okay, and actually before our queue information, I want to just point out these are all of our device extensions that the device supports, right? So these are all names of extensions we could load. Here is our queue family properties, right? So remember before I was talking about how we have these different queue indices that support different types of operations. And so basically what we're looking at here is these queue properties. The 0 is the index, right? So index 0 supports graphics, compute, transfer, and something called sparse binding, which we're not going to get into just yet, right? So this particular queue supports operations for all of these, whereas queue index 1 only supports transfer and binding, right? Sparse binding, whereas index 2 on this particular device supports compute, transfer, and binding, right? And so we want to bear in mind that for transfer queues, for example, we'd probably want to use one that was dedicated to transfers instead of one that was also using graphics or compute. We probably want to make sure that this is on a different queue so that we can actually use one of those instead. Now, one other thing I want to point out is this is a queue family index, okay? So each of these families can have a certain number of queues available to them. So this particular queue family has 16 queues that we can create out of this pool, whereas this one only has 2, and this one has 8, okay? And so we'll need to know all this information when we go to create lots and lots of queues down the road, but for now we're going to keep things simple, and we're just going to create a couple of these. But I wanted to show you guys this just so that you kind of understand what's going on there. The other thing I wanted to point out is we have our memory information. So our memory heaps gives us the size of the memory, how much is used, any particular flags telling us what kind of memory it is. So device local means that it's local to the device itself or on the GPU, whereas I believe it's shared is actually shared between the system and the GPU. So there's all kinds of properties in here to look at. I highly encourage you guys to run this Vulkan info. And one other thing that you can do, by the way, if I clear this, you can, if I change to desktop, right, and I say Vulkan info, and then I use an angle bracket, and I output to vkinfo.text. This is basically saying, instead of writing this to the screen, stream that to vkinfo.text and put it on the desktop, right? So I'm going to exit this and open up. I've got this on another screen here, but now I have this available in text, so it's searchable and whatnot. So you guys may want to run this. I think I mentioned this in an earlier video too, but I just wanted to sort of retouch on that. Okay, so with all that in mind, we are going to keep what we call a transfer score, and for every queue that we find, we're going to increment this transfer score, and then we want to actually use when we actually go to obtain our queue index for our transfer operations, we actually want to use the one that has the least amount of these, meaning the least amount of these queues that are supported. That way it's pretty much guaranteed to be a dedicated queue to transfer operations if that is available. So first off, we check the graphics queue, right? So we do this by checking the flag and doing an AND bitwise operation against the VK queue graphics bit. And then if it passes that test, then we say the queue info graphics family index is equal to I, and we increment the transfer score. We do the exact same operation for compute operations. Okay, we just use compute bit instead, and then set the compute family index, and again increment the score. The transfer queue comes last, and basically this says we take the index if it is the current lowest. So this increases the likelihood that it is a dedicated transfer queue. So if the current transfer score is less than the minimum transfer score, which is up here, 255, right? We sort of define that up here. Then we'll go ahead and use this one. And so as we loop through these, it's going to continuously take the lowest scored family and use that as the transfer bit, or the transfer queue index. Okay. And one more thing is the only thing that we did not check for is presentation. But presentation, the queue flag is not actually part of that. We actually have to query that specifically by calling this vk get physical device surface support KHR. And this basically returns a Boolean, right? So a vk bool 32, and then we say if that's set to anything other than 0, then we set the presentation index to 1. Okay, and so all of these will fill out ultimately these things here. Okay. The next thing we're going to do is we're going to print out the info about the device. So we started this table up here saying, okay, these are the different queues that it supports, and then the name of the device. So right after the loop, we are going to print the info about the selected device, which is basically the outputting the last thing selected. Okay. And so basically this is just checking these to see if it's -1, and it's either going to print a 0 or a 1 for all of these. And then these are just sort of formatted and spaced out in such a way where it'll line up in a nice, neat looking table in our console. Okay, so now that we have the queue information, now we actually need to go through and say, hey, does this actually meet the requirements that we've set forth? And the code for this is, I'm not going to lie, it's a bit ugly. There are probably better ways to do this, but for now I want to keep things simple, and simple isn't always pretty, right? So what we're going to do is we're going to start off with this check, which basically checks to see, okay, well, so if graphics is not a requirement, or it is a requirement and we actually have an index for it, right? So this same switch is going to be checked for graphics, present, compute, or transfer, right? Meaning either it's not a requirement or it is a requirement and we have a family index for it. So if that's true for all 4 of these types of operations, then the device so far meets requirements. So we are going to, again, print that information out, okay? Next, we are going to query the swap chain support. And we actually do not have a method in place to actually do this yet, so we are actually going to want to query our swap chain support. So what I'm going to do is, before we actually get too in-depth with that, I'm going to come back out to our Vulkan device and put this here. Vulkan device query swap chain support, okay? And it takes the physical device, the surface, and the swap chain support info, and it sets that, right? An out pointer to that, okay? And so I have that. I'm not going to fill it out just yet. We're going to come back to that because I'd rather finish this function and then come back to it. So let's go ahead and do that. So right here, we are going to query these swap chain support, okay? So this is just a simple call to say, whoops, this needs to be inside that if check. There we go. So this is basically going to say, find out what support the device has for our swap chain that we're going to need, right? And then we'll use this to determine if it meets our swap chain requirements, okay? So now that we have this plugged in, let's go ahead and fill that out. So this time I'm going to do this right after Vulkan device destroy because it is a public function. I want this here towards the top, okay? And the first thing that we're going to do is we are going to detect what the surface capabilities are for this particular device. So we call vk get physical device surface capabilities KHR. Okay, we pass it the physical device surface and a pointer to our out support info capabilities. All right, and if you recall, that is this structure here. So we're going to fill this guy out, and then we're going to fill out these guys next. Okay, so we first do that, and then the next thing we're going to do is we are going to obtain our surface formats, and we're going to do that by vk get physical device surface formats KHR, and it's going to first obtain the count, and then if that count is not 0, then it is going to do a check to make sure that the formats is not already created, right? Which we initially would set this to 0. This would be zeroed out by default. So if it's zeroed out, that means we need to actually allocate space for this. And then we go ahead and say, get our physical device surface formats, right? And so we have our first call here to get the count, our second call here to actually fill out the array, okay? And so from there, that is our surface formats. We just obtain those. And then our present modes works almost the exact same way. So we just make a different call. So we have our present modes calling vk get physical device surface present modes KHR, and it fills out present mode count. And then if that is not 0, then we go ahead and check to see if the array has already been allocated. If it has not, we go ahead and perform that allocation, and then we go ahead and call that function again, this time passing a pointer to that array. Okay, so the reason for this and the reason for these checks and whatnot is because we're actually going to be calling this function from multiple places multiple times. And the number of these things aren't going to change, but some size information might change in terms of resolution. So again, I'll get into this when we actually get into swap chain, but I wanted to sort of quickly cover this now. So our query swap chain support basically just fills out that structure, and then from there we can continue on. So I'm going to go ahead and sort of just minimize this block of code here and go back down to where we were calling it. Okay. So the next thing that we're going to do is, now that we have the supported swap chain capabilities, we are going to check that against what we actually require, right? And so first off, if we have no available image formats, which is what these formats are, if it's less than 1 or we have no available present modes, then what we're going to do is we're going to go ahead and make sure that these arrays are actually freed. And then we are going to just basically boot out saying, hey, you know, there's no swap chain support present for this device. We can't use it. Okay. Next, we're going to take a look at some device extensions. So here we are going to say if we have extensions that are part of our requirements, then we are going to go ahead and obtain a count of the available extensions, right? And if the available extensions count is not equal to 0, then as we have done in other places in code, we are going to go ahead and obtain those extensions. Specifically the device extension properties, right? So we're going to fill out an array of these properties here, okay? Next, we are going to iterate the required extensions and check them against the available extensions. And similar to how we did the validation layers in the initialization, here we are going to basically perform the same thing, but for our VK extension properties, right? So any of them that we require that we don't find, we throw an error saying, hey, this is required but not found, and then we free up that memory and return false saying, hey, we can't use this device. Okay. And then finally, we go ahead and free this available extensions just to not leak that memory. Okay. And I just realized I put that on the wrong line. Let's fix that. Okay. So right after we end our check for the device extension names, this is how we check for individual features, right? So our requirements, if they say that we require sampler anisotropy, and that is not available in the feature set, then we say, okay, hey, we require this, but we don't support it, skipping the device, return false. Okay, so this is an example of how you can check for that. So if we get to this point and the device meets all requirements, we are going to go ahead and return true. If we get past this point and for some reason we've failed every check, for example, we fail this check here, then we are going to return false, saying we cannot use the device. Okay. So that is the long-winded physical device meets requirements, and you can kind of see why I might have split this up into a different function, is because it's quite long-winded. So I'm actually just going to snip this down just for a minute so that we can actually not have such a tiny scroll bar over here on the right. Okay, so back in select physical device, we left off here at our queue info, which we said was going to be filled out by our call to device meets requirements. So next we check to see if the physical device we currently have meets the requirements. And we take all of our extracted information here, pass it through, right? And then we also save off the context device swap chain support, which we don't currently have. So I will go here to Vulkan device and add swap chain support to the device to fix that problem. Okay. We're almost done with physical devices. I did warn that this was going to be a little bit long-winded, and it is. So the next thing we're going to do is check to see if the result is true, meaning we have a device that we can actually use. Okay, and if we do, we are going to print out some information about that device, just as sort of a way for us to verify within the console that the device is good to go, right? So I'm going to go ahead and print out the name of the device, and then also its device type, so whether it's integrated, discrete, whether it's virtual, like if you're on a virtual machine, if it's CPU based for some reason, or if it's just some unknown weird type. The next thing we're going to do is we're actually going to obtain the driver information. So Vulkan allows you to pull the GPU driver information and the Vulkan API version that's being used. So we're going to extract both of those things. And this basically just pulls the driver version and then passes it through this VK version major macro, which is provided to us by Vulkan. It basically takes an integer and extracts the major, minor, and patch version out of it. So we're going to do that for driver version and API version and then print that to the console. Next, we're going to go ahead and print out some memory information. We're not saving this off for now, but eventually we probably will need to. So it basically goes through each of our memory heaps, which I showed you in the Vulkan info, and prints out how big those are in gigabytes. Now, the size that's given to us here is in bytes. So in order to get the gigabytes of that, we will convert it to a float and then divide by 1024, 1024, and 1024 to get that conversion to gigabytes, right? Because that's really what we kind of care about at this level. And then if the memory type is local, meaning it's dedicated GPU memory, then we print out that it's local. Otherwise, we say it's shared. And again, that will come into play later on, but for now, we're just printing it out. We can always extract this information and save it off later if we have to. Okay. Finally, at the end of this, we are going to set some different things on the device, which we actually are missing a good bunch of these properties, so we're going to have to go and add them. But we're basically going to copy over information from the physical device that we actually need to know. So the physical device, for example, we're going to copy that pointer over. We're going to take the indices of the graphics, present, and transfer queues. If we need compute, we'd set it here as well. And then then we'll also take the properties, features, and memory that we extracted further up the chain up here, and we'll save those off as well so we don't have to requery for them later on. Finally, we are going to break the loop. So if we get here, this means that we have a device that we actually want to use, and we're going to go ahead and break that loop. So just before we exit out of this and set these things up, I want to just complete this function because we're almost there. So next, outside of our initial check to see if we had, or I should say our initial loop to see if we had physical devices, we're going to check to see if we actually picked one, right? And so we're going to say if this is still 0, which is what it would have been initialized to, then we have no physical device that meets our requirements and we need to return false. Otherwise, we have selected a physical device and we can just return true. Nice and simple, okay? So let's go to the device, and the first thing we need to do is create a graphics queue index, present queue, and transfer queue index. And so on the device, right below swap chains port, we're going to add those 3, okay? And then we also have our swap chain support already. We are also going to want to store off our properties, features, and our memory, okay? And you'll see that that resolves those errors, okay? So, with all that said, I believe we should be able to build. Nope, looks like I missed something. Oh, right, okay. We weren't quite done up here, okay. So Vulkan device create, this requires a Boolean, and we're not returning a Boolean. So we actually need to go ahead and set that up next. So for right now, in this video, I'm just going to return false. There's still more that needs to be done here, but for now, there we go. Okay, and I'm going to go ahead and run. And now we have all of our information printed out for us. So what we're looking at here is we see our surface has been created, so that's good. We see that our particular device supports a graphics, present, compute, and transfer queue, and it's a GeForce RTX 2080 Super. It says our device meets queue requirements. it gives us the indices of those individual queues, right? So our graphics family is using 0, which is good. That's the only one that supports graphics. We don't want anything else using that. Present is on number 2. Transfer is on number 1, so that's that dedicated one that we wanted. And then compute is also on 2. So that looks good. Here is an example of our debugger working. So we have an info message here saying disabling implicit layer, VK layer, OW overlay. This is from a Vulkan extension that is installed. I think it's the Overwolf application that is actually doing this, that I have installed on this machine. So if you have that installed, you may see this message, otherwise you may not. But this is an example of our debug layer working, so we know that that's good and working. Here's where we have our selected device. GPU type is discrete. Here's the GPU driver version, the API, some memory information, shared system memory, which is only 32 gigs, which is interesting, because this machine actually has 64, but I guess maybe it can only use 32 of that. Our local GPU memory, so we have one block that's 7.82 gigs and then one that's like 1/4 of a gig. And then we have physical device selected and then render initialized successfully, right? And then all of our other information here. So we are good to go. We know that this is all working properly as expected. So that is physical device selection and surface creation. And so there's a lot in this video. I realize this video is quite a bit longer than the others before it, but I felt that it was needed to be kept in the same video because it's all very closely related. So this is a good stopping point though. Next time we will go ahead and create our logical device, which is what we're going to use for 99% of our other Vulkan calls throughout the system. So thank you guys so much for watching. If you haven't already, consider subscribing, hit the little like button. Also make sure you click the notification bell there to get notifications when new videos in this or other series drops. And thank you guys for watching. I'll see you next time. Bye.